Welcome back. So the next speaker doesn't need any introduction. I'm going to talk about Choriocapillaris flow and power laws, and that sounds like a funny topic, and actually most of this talk doesn't have to do with ophthalmology. How do you like that? So it's a little refresher. So the first thing I want to talk about is normal distribution. So if you look at the tallest male who's ever been recorded in human history was 2.72 meters high. And the shortest one was 0.57 meters, which is kind of amazing that was a man, right? But the ratio is 4.8 to 1, which isn't that big. And if you look at the height of people as plotted on a graph like this, you see that it follows a Gaussian distribution. And the Gaussian distribution has certain characteristics. We can look at standard deviations, and that 68% of whatever you're looking at is within one standard deviation, and 95% is within two standard deviations. And a lot of our statistics that we use in medicine, particularly inferential statistics, is based on this idea. If you look at the biggest city in the United States, that's New York City. And if you look at the smallest one, one. Now, really, there's not that many cities one. This is kind of a fake thing, but because it takes about 25 people to make a town at least. But if you look at that ratio, it's 8 million to 1, right? And if you plot out the size of cities versus how many they are, it has this kind of curve. And if you're not used to looking at that curve, that's a kind of a strange-looking curve. But as it turns out, as you'll see, that this is one of the biggest or most important kind of curves in nature. If we look at the population in the United States, again, the population of cities at least, then we try to figure out what's the average population of a city. We come out to 24,000. But curiously, the standard deviation is 50,000. So if we go back to our inferential statistics idea that we have a curve and look at two standard deviations, we get the idea that 95% of cities fall somewhere in between minus 76,000 people and plus 124,000. But it's hard to figure out how you get a city with minus 76,000 people. And that's because we're trying to use the wrong kind of statistics or the wrong way to look at things. In addition, if we go back and look at New York City would be 160 standard deviations above the mean, which means that New York City is statistically impossible. So we're trying to use a non-normal distribution and use statistics for a normal distribution, and that's clearly a wrong thing to do. So that's a kind of a special curve. And there was a guy who really started the interest in this, and his name was George Kingsley Zipf. Now that sounds like some kind of British name, but he actually was at Harvard in the 1920s. And he looked at words and how often words were used in language, and particularly English language. And he found that it followed a curve just like what we're talking about. And the curious thing is that the most common word in English language is used twice as often as the second most common word. And the most common word is used 3 times more often than the third most common used word. And the 10th most commonly used word is used 10 times more often than the 100th most commonly used word. So that's a kind of a strange mathematical relationship among words in the English language. The other strange thing is if you plot that out on a log-log plot, it comes out to be a perfectly straight line. This is for word use. So that curve, actually, if you plot that out, and if you see that curve, you plot it out on a log-log plot, it comes out to be straight. And that's not just true for English language. Here's the same plot for 30 different languages on Wikipedia, and you can see that line is straight for 12 log units. So the structure of human language is based on a kind of a mathematical relationship just by natural circumstances in which it follows this sort of weird kind of curve that if we plot on a log-log plot, it comes out straight. We say, well, that's just humans. Maybe humans are arranged like this. But, I'm going to talk about one thing. If people actually looked at how porpoises communicate with each other, and the squeaks that they use actually follow a log-log plot too. So they have a kind of a language of their own, follows the same thing. There's a characteristic of this that's called scale invariance. And if we were looking on that log-log plot and we were a little ant, we wouldn't really know where we were on that plot because no matter where we were, the slope of that line would be the same thing. So no matter what scale we look at, it's the same relationship. This really got Mandelbrot very interested, and he wrote his PhD thesis on Zipf's law. And as you realize, he went to look at a lot of other things. This is the price of cotton, and this is one of the examples that he used in one of his earlier papers. And if you look, there's lots of little motions, and maybe not such bigger or medium-sized motions, and very few large motions. And the curious thing is that there's a kind of, if you plot that out, it actually follows on a log-log plot. And it doesn't matter what unit of scale you use. You can look at a big unit of scale like 1 year, or you can look at smaller like 1 day, or 5 minutes. You can't tell a difference because those jagged lines still form that same kind of scale invariant sort of process. So he was very interested in the self-similarity across units of scale. And he noticed that lines really weren't one dimension, but they weren't 2 dimensions either. So he thought they were a fraction of a dimension in between the two. So he called that fractional dimension a fractal, and that's where the word fractals come from. He made computer graphics at the time were very primitive, so he used to make these printouts. Then that was rejected by many mathematicians because they thought this was some kind of artifact. So he published a book about the geometry, fractal geometry of nature, and we all recognize now there's many different kinds of fractals in nature, and it's all built up on this self-similarity or scale invariance. And it's been used in art. This is, as you know, a famous Japanese print. Then you can look at the little waves, make up bigger waves, and make up bigger waves. Fractals are even in Japanese art. Blood vessels have a self-similarity to them as well. And you can imagine I just drew this kind of fractal kind of branching of blood vessels. It's a very orderly way it's drawn. Blood vessels really aren't found like that. But on average, they kind of average out to this. And there's a mathematical relationship about how branching happens in blood vessels in the eye in terms of the radius of blood vessels. And also in the eye, the length of any given segment has also been shown to mathematically be related to the radius. And this holds true for every level of branching that happens in retinal blood vessels. So if you look at all of these things, the log of the number of the length of blood vessels versus the log of the radius, or you look at the log of the numbers of branches versus the radius, any of these things, they all follow a straight line on a log-log plot. So the way that we're kind of made is according to that way I showed you before about how language is made or how other things were made in nature. It follows a log-log plot. We go back to this price of cotton, and you might remember that I showed that those lines, or I mentioned that those logs are the size of the motions of the price of cotton versus the log of number also follows a straight line. So this guy, Purbach, which sounds like a funny name, but that's what his name was, he modeled avalanches on a computer. And the way he did that is he just had grains of sand fall down in the model of this computer. And then if it reached a certain height, it fell down automatically. And those grains fell on other grains. And you can imagine as the grains kept pouring onto this thing, you'd get little avalanches and bigger avalanches and whatever. So he left it run overnight, and then he looked at the number of avalanches versus the size. And guess what? It was a straight line on a log-log plot. This is a kind of amazing thing that just adding grains of sand to make an avalanche made a straight line on a log-log plot. So they went to actually look at real avalanches, and you know what? If you look at the log number of avalanches versus their size, it follows exactly a straight line. And when they do make an avalanche, the pattern they make is a fractal in terms of its pattern. If you look at earthquakes, same thing. The magnitude of an earthquake on a log-log plot is related to the log of the number of earthquakes. If you look at wars, same thing. The log of the number of wars is proportionally a straight line on a log-log plot to the size of the war. And you can look at banking crises, corporate bankruptcy. You can look at how often a potassium channel is open in terms of the number of times that it's open per second. Follows a log-log plot. It's a straight line. And this is the same thing is true for volcanoes, solar flares, forest fires, traffic jams. All follow that interesting curve. And that's really how nature works in a lot of ways. And there's a book by Purbach, which it's a very short book, it's very nice to read, How Nature Works. It's really devoted to this topic. So let's talk about choriocapillaris. So the choriocapillaris is a mesh of blood vessels, fairly uniform. But if you look at the back surface of this mesh of blood vessels, there's arteries and veins that set up channels or set up pressure gradients, and we think of it as having a lobular flow. And this is what Hay-Ray showed. The lobular flow, and at least in the human eye, the lobules are about 1 millimeter in diameter. They're fairly large. Maybe some are only 0.5 millimeter, but they're fairly large sort of things. But here's a choriocapillaris image of a 28-year-old. You can see there's flow voids or signal voids present that are smaller than a lobule. And what's it doing in a 28-year-old? Well, to do that, I did a study on a number of patients. You can see 104 eyes of 80 patients. Their mean age was 71 years. And then here's an example of an older patient with pseudodrusen. And you can see there's many flow voids. And you say, well, that just looks like noise. Maybe that's just noise. Maybe it's a flow. Who knows? Well, one thing you do is maybe average together. But here's an example of cars being averaged together on a street. You could look at how the separations of the cars are and get an estimate of how dense the traffic is. Maybe we'll average that together, get rid of some of that variation. Then you can see here you average 5, and then finally 20, you can't see the cars anymore. So actually averaging loses the flow information in many instances. Really, this contains the flow information itself, and averaging gets rid of some of that information. Those gaps are what's missing. If we look at them, the size of the gaps versus their number, you can see it follows that kind of special curve. In fact, there's a straight line curve in a log-log plot. So those defects in the Choriocapillaris flow follow that same kind of pattern that we see in nature. It's kind of strange, right, to think about that. That the way we're structured and the defects that we have are kind of in a pattern that's seen in many other instances. Also note that we really can't take averages and means of those flow voids because it doesn't follow a normal curve. It follows this kind of curve. If you look at it, remember, this kind of translates back into that line sort of intercept equation from high school or from junior high school. And if we look at the slope of that line, it's related to in this group of patients to age and hypertension. And this offset is related to age, having late AMD, or having in the fellow eye, or having hypertension. So if we look at one eye, we can kind of tell if they have late AMD in their other eye based on their choriocapillaris. And you can see the people with the biggest ones are people old age, those who have pseudodrusen, and those who have late AMD in their fellow eye. Now, this power law characteristic has been found in microvascular flow and other systems, but they had to actually kill the animal after giving nanoparticles to look at where they got occluded in blood vessels. And it's the first time we'd be able to see this kind of flow pattern in living subjects just by looking at the choriocapillaris. So all of these things are smaller than a lobule. We used to think about lobular flow in choriocapillaris. Now this is much more common as sub-lobular flow problems. And it's related to systemic and ocular factors. Well, how can this occur? A paper by Rob Mullins and also Christine Curcio and I actually, on a different paper, showed that choriocapillaris segment occlusions are fairly common. But you could expect that that would decrease the flow around that, much the same way that if we block off traffic, it causes a bigger traffic jam than just where the traffic is occluded. As long as there's another occlusion or another stoppage or slowdown of traffic or blood flow anywhere near that, if that multiplies over time, it's going to end up making a power law distribution. Well, there's one more cool thing about this, and that's that we can model this mathematically in a way that may not be totally obvious at first. Many kinds of things in a phase change make us kind of a structure automatically, and that's part of this kind of concept. When you get a phase change, all the changes happen near it or in a power law kind of distribution, and they make fractals. And this self-organized characteristic happens just in nature automatically. So we look at a lot of different phase changes like water melting or water freezing is a phase change. When those molecules start to do that, they do that in a fractal way, and they also aggregate in ways that follow power law distributions. And the same thing happens when iron becomes magnetized. Remember that magnetism is based on a rotation of electrons. And inside of a ferromagnetic material, there's lots of little dipoles, and we can make them get arranged in a certain way if we put an external field on that. But if the temperature above that is greater than the Curie temperature, they won't align because there's too much energy. They're too wild. You can kind of make that to make an analogy to dogs. If dogs are very energetic and run around like crazy, it's hard to get them to be organized. But if you get them to calm down and make sure their neighbors are kind of calmed down, then you can get them to be ordered. So atoms are kind of like that. So to get dogs not to be excited, we have to have some kind of inducement to make them become calm, and you have to make their neighbors become calm, because if one dog is surrounded by dogs barking their head off, they're going to bark too. But if nobody barks, then nobody barks. So atoms are kind of like that too. So if we reduce this down to near the Curie temperature, they start to organize automatically into areas where the dipoles are aligned. And these things follow a power law distribution. So to make magnetic dipoles align, you need to have an external field. The temperature has to be low enough so it doesn't. and you have to care about what their neighbors are doing. And that thing, that whole model is called an ISSOCT model. It's actually a fairly simple model to make. So that would be interesting in its own right, but people then later adapted the ISSOCT model to a number of things, like epidemics, or how birds flock. You know, these starlings, when they fly like in those bizarre patterns, it's all based on each starling only looks at its nearest 6 neighbors and controls its flight only on that basis. But somehow they end up making this weird flocks that have very amazing patterns. So it was first used to model magnetism, now used to model a lot of other things. Thomas Schelling created a model for racial segregation based on this. And he really re-derived the ISSOCT model and somehow won the Nobel Prize for that just by looking at racial segregation based on that same idea. But we can apply that same concept to modeling choriocapillaris flow, and you can see this progression of changes that happens over time that emulates what happens as people get older. They get more and more of these kind of defects. And you can make it into a movie, and this is a kind of a movie of an ISSOCT model of what a person would look like as they got older. These black zones come and go, but you can see over time they aggregate and make bigger ones. At any one step you stop this, it follows a power law characteristic. So we know that there's an RP and choriocapillaris interplay there, and if you get atrophy one, you end up getting atrophy other ones. So to save time, I'm going to skip right to the last slide. That signal avoids power law distribution in humans. It's associated with age, hypertension, and AMD in the fellow eye. It's possible, I think, to mathematically model this, and we can look at the health of somebody's choriocapillaris and maybe infer the health of them as a person in terms of biological age or biological health. And that late AMD, if you think about it, may be a phase change, just like atoms are becoming magnetized. Maybe geographic atrophy or CNV is really kind of like a phase change that we make before we make our final phase change. Okay? Well, that's the end of the talk, and I thank you.